Okay, this next video is for AP Physics 2 only. What if you have a circuit with more than one battery in it? Here's a common example. This is a car where you have a dead battery and then you're using another car to give it a jump start. So in this type of problem, you have to use Kirchhoff's rules in a very specific way. And if you can do that, then you can set up equations. You get a bunch of equations and then you have to solve them. It is totally unreasonable on the AP exam or on one of my exams to ask you to both create and solve these equations. It would take way too long, and it has a lot more to do with algebra than it does physics. It's entirely reasonable to ask you to write the equations but not solve them. And so I'm going to show you how to write these equations, then we'll go ahead and solve it anyway, just so you can see how that might be done. But the goal here is to create the equations that you could use to solve the problem. Let's do it. So in a jump start, you hook a live battery to a dead battery, and you then send the current through the starter in order to try and get your car to start. Dead batteries have a much higher internal resistance than live batteries, so these numbers are pretty realistic. To create the equations needed to find the currents in each branch of these circuits, we're going to use the junction rule and the loop rule. For the junction rule, you need to label each of your currents and the direction they're going, and you have to guess, but it doesn't matter if you guess incorrectly. That'll come out as a negative sign in your final answer. To make sure you don't make any sign errors using the loop rule, you have to traverse each loop in the same direction, either clockwise or counterclockwise. Just pick one. The rules then are as follows. If you go over a resistor in the direction of current, that's a voltage drop, and the change in potential is minus IR. If you go opposite the direction of current, then it's like you're swimming upstream, and the voltage is going to be plus IR. If you cross a battery in the direction of the battery, it adds to voltage and you get plus epsilon. If not, it's minus epsilon because you're fighting the battery as you go across. Follow these rules and any incorrect guesses you make will automatically come out in the math. So let's try it. Labels will make things a lot clearer, so let's give every circuit element a name and name each corner and junction, starting in the bottom left-hand corner and going around with the letters of the alphabet. That done, pick a junction and label your currents. Again, it doesn't matter which direction you pick. If you choose wrong, it'll end up being negative in your final answer. However you did it, use the junction rule to set the currents in equal to the currents out. Time for the loop rule. Let's create our first equation by making it explicitly clear which loop we're doing and what direction we're going by labeling it using the letters. Starting in the bottom left corner, we cross epsilon 1 in the direction of the battery, so that's positive. We cross resistor 1 in the direction of current, so that's negative IR. We then cross resistor 3 also in the direction of current, that's a negative IR again, and then we loop around back to A without hitting anything else. This has to sum to 0 because that's what the loop rule says. The total voltage around a circuit sums to 0. Time for the left loop. The first two terms are the same, and I2 R2 very similar. But here we cross the dead battery backward, so its voltage contribution is negative. In the right loop, we cross the dead battery in the right direction, but we cross resistor 2 against current, so its voltage contribution is positive. We then cross R3 with current, getting minus I3 R3. And there you have it. Those are your equations, and that's probably what you'd be asked to do on the AP2 exam. Let's go ahead and solve this anyway, and to do that, let's give each of these equations a label. Then, we pretty much always start by substituting the junction rule into one of the loop rule equations. Let's substitute it into equation 2. Plug it in, distribute, group like current terms, and name it equation 5. Next, let's solve equation 3 for I2. And substitute that into our new equation 5. As bad as this is, it looks worse than it seems, so let's substitute in the numbers given in the problem and go from there. The voltage terms end up combining, and we get it divided by 1, so except for its unit, that just goes away. And I have a typo in the previous line, so let's kill that. With all our numbers, we find I3 equals 185.6 amps. which we can plug into equation 3 to get I2 equals 1.14 amps. And now we can plug I2 and I3 into the junction rule to get I1 is 187 amps. Note that none of the currents ended up being negative, which means my initial guesses on directions happened to be correct. And please remember that I might ask you to come up with these equations, but I'm never going to ask you to solve them on any kind of a test. See you next video when we talk about how capacitors behave in circuits.